Hello, grade 12s, and welcome to this fairly brief introduction to calculus. Okay, so there's so many cool things in calculus, and we're just going to touch on some of the ideas here without being too laborious. But let's start off with some more kind of grade 9, 10 concepts, and let's draw ourselves a graph of f of x equals x squared plus 1. Okay, easy enough. You can draw that, and please draw it, but fairly rough. Doesn't have to be perfect. I haven't even put the numbers on the axes. We know it's going through 1 and, it's sort of that shape. Okay, good enough. Now, before we get into anything too calculus-y, let's just work out the gradient between 2 points. So these 2 points on the graph, A and B, they could be anywhere. Let's put A there, B there. And let's say if we were to draw a line through there, what's the gradient of that dotted line? So in some ways, it doesn't matter that they're on the graph, but it does because A, wherever we move it, is going to be on that graph, B likewise. So on our graph, we've got 2 points, point A and B, doesn't matter where they are, and we just want to find out what's the gradient between those 2 points. Well, that's easy enough, because to work out gradient, I'm just going to put A, say, over here, and B somewhere over there. Well, to work out the gradient, we just work out rise over run. Okay, so that's easy enough. Let's capture some of this thinking, actually. It's so good. So the gradient is rise over run. And then we can work out anything. So, well, maybe not anything, but we can work out the gradient at least if we're given those 2 points. So let's specify points A and B, but only in terms of their x values. So I'm going to put point A at, let's make the x value 3. And then I'm going to make my life easy. I'm going to make point B just 1 unit away. So they are measuring perfectly, not really. That B is 1 unit away on the x-axis. So therefore, it's 3 plus 1 gives me 4. So I've ensured that my run is 1 because 4 minus 3 is indeed 1. Okay, and I just wanted it to be 1 away. Just make, sometimes we make our lives easy. Sometimes we make it more difficult, but let's make it easy. Okay, well, that's easy enough. Now we just need to work out the rise. Oh, well, now it's useful that the 2 points are on the graph because we can work out the y coordinate of point A. Well, to work that out, we just need to put in 3 to our function. So that's easy. 3 squared plus 1. That gives us 10. Okay, so we work that out by working out f of 3 to work out that the y value is 10. And we could do the same for the y value of b. We could just substitute in, we were 1 away, right? So it was 3 plus 1. Well, that was 4, we already said that. So f of 4 and 4 squared plus 1, well, that's just 17. So now when we work out what our rise is, well, to rise from 10 to 17 is to rise by 7. But let's capture some of our thinking in this gradient formula because this is kind of what's important here is this idea of gradient because that's the heart of where we're going to today. So let's put that in and say, well, to work out the 17 minus 10, we said f of 4 minus f of 3, which was the 17 minus 10, which gave us a gradient of 7. In other words, the average gradient from A to B is 7. The gradient from A to B is indeed 7, and it was on this graph. Now, these 2 points could have been anywhere on the graph. We could have put A there, B there, and said that the average gradient of this graph from A to B is whatever this rise of a run is. It looks approximately 1 here. And the gradient could have been a negative gradient. It could have been over there. Doesn't really matter. We're just working out the gradient or average gradient between 2 points. And this is something we've been doing for years now. So that wasn't too difficult. It was just rise over run. That's what we've been doing. But let's make this slightly more complicated to allow us to do something a bit more interesting. Okay, so point A, I said I put at a particular x value. So I put it there and I moved this until x was on 3. And I said, cool, that's where my x value is. And then I said, I want b to be 1 away. So I'm going to put it x plus h away, where h is 1. So I want to put it 1 away. Okay, so instead of talking about our run as our run is just the distance h. In our case, it was 1. So we've got from A to B, the x distance, the run is 1. Okay, so x to x plus h. Again, I want to capture this because it's such beautiful stuff, that m is still rise over run. Nothing's changed there, still that same concept. But to work out our run, we said, well, we're running by h. So I'm just going to put h as our denominator. Okay, now let's work out what our rise is. Well, we had to work out the first y value of a. So what we did was, we said, let's plug that in, and I'm just lining these up a bit more neatly now, and said, well, if we put x in, if we put 3 in, we got an output of 10. We worked out what f of x is. Okay, so that was what the first value was. And then to work out our y value of b, we subbed in our next point, which was 4 in our example. But I'm talking about this, I'm referring to this as x plus h. So what we're going to substitute in is f of x plus h. Okay, so therefore our rise is just the top value minus the bottom value, right? B minus a, their corresponding y values. So our rise, instead of calling it rise, I'm going to call it f of x plus h minus f of x. So now when we look at rise of a run, we can talk about this as f of x plus h minus f of x. Same thing that we did. Let me see if I can... sometimes I'll get better at these things. There we go. Same thing that we did over here is what I'm trying to refer to, is what we're doing over here. We're just doing it in a more general way. Okay, so f of x plus h minus f of x over h. That's another way of talking about our gradient. So that's all well and good, but we seem to have overcomplicated things as we are wont to do, and talking about our gradient in a more complicated way, but it just starts from a starting point now, x. Okay, so hold that in mind, and let's see what that allows us to do. I'm going to clear all of these things from our little graph here, and rewind and try a new idea now. And this is the calculus part coming in. We've got a graph. We've got a point A somewhere on our graph. Now what we want to work out is, what's the gradient of the tangent at that point? In other words, we want to work out the gradient going through one point, not two. Well, this doesn't seem to fit in. Where's our rise and our run now? Because we need 2 points to work out gradient. Rise over run, right? So let's see how we can do this. I'm going to say, well, we know how to work out gradient between 2 points. There's our line through A and B. We worked out rise and run. And then we said, no, well, let's talk about it as something a little bit more complicated in these terms here. Well, that's fine because we've got 2 points, but that's not our tangent. But hang on a second. I've got a great idea. And let's just move B until it's right on top of A. Oh, well, that's going to work out perfectly because look at that gradient now, that dotted line, and I'm going to add the tangent. Those two lines are the same. I don't know if you can see that, but no matter which one, the average and the tangent are the same. So that's all well and good. All we need to do is say, okay, start off with B over there and move it till it's right on top there. But wait a second, what's our distance of H now? Well, H would be 0. And wait, rise over run, that's all well and good, rise over run. So our formula over here, this one just up here, is going to be dividing by 0. Seems to be a problem, but that's what we're going to see algebraically next, how it's not so much of a problem. But let's stick to those concepts because they allow us to get somewhere. So I'm going to call this new idea f prime x, or the derivative. The derivative's still gradient. It's just gradient at one point. So it's still going to be f of x plus h minus f of x. Everything divided by h. But now what we're going to do is use this concept to say, okay, so point B is over there. F of x, or x plus h, f of x plus h. There's point B. And I'm just going to work this out, but I'm slowly going to move this and make h smaller and smaller and smaller and smaller and smaller until h is 0. I'm not saying h is equal to 0. We're just going to keep moving until h is 0. That tangent, or that gradient over there, is getting closer to the tangent until eventually it is the tangent. And this could have been anywhere. A could have been over there, and B could have been over there. This shows it quite nicely because there's the tangent, this dotted line here. So if we move B until it gets closer and closer and closer, we're getting closer and we're getting eventually that average gradient will be the tangent itself. So we're starting there and we're just going to make h smaller and smaller and smaller. So we just need a bit of notation, that's all. And this notation is going to be, we're going to work out the limit as h approaches 0. We're not going to let h be 0, it's just going to get closer and closer and closer. But it's the same formula we're just working with. The derivative is just the gradient at a point. It's the gradient, but we're going to make h smaller and smaller and smaller and smaller. What a beautiful idea. And we'll figure out how to do this algebraically, and we'll get more in depth with this and more comfortable as we go along. But there's our key idea. Really, there's that key idea visually, that we're going to work out the gradient between 2 points until eventually kind of those 2 points are on top of each other. Okay, there it is. Rise over run. That's all it is. Rise over run, and then bang, it gets in. Okay, well, that's what calculus is for now. I mean, there are lots of different aspects to it, but that's just my way of kind of getting us into it. As I said, the next one we'll work out some rules to get there a bit quicker. We'll work with these and do exciting and interesting things, but I'll see you in the next one.